Hey there. In this video, we're going to talk about random variables and probability distributions. All right, so let's take a look. So what is a random variable? A random variable assigns a numerical value to a random process. So I'm going to perform some kind of probability experiment. I'm going to do something random, and I'm going to assign a value to that. So one of the most basic examples is rolling a die. Right? So I roll a die, and what value am I going to assign? Well, the most obvious one is to just take the number of pips that you see on the top of the die. So here the value would be 6. Here would be 4. I could get a 1. Right? So that's an obvious random variable to choose. Is that the only one I could do? Well, no, there are other options. I could measure the distance that the die landed from the, I guess in this case, the edge of the screen. Right? We could measure that distance with a ruler. Right? I could measure the time that it takes for the die to come to rest. Those are other random variables that I could assign to this die roll. Now, I don't need to roll a die. I could choose a person, right? And what kind of random variables could we imagine? Well, I could measure their age, salary, I could measure their weight or their shoe size. All these are numerical measurements based on this random process. I'm choosing a random person, and I can assign a number this way. And that makes those things random variables. Okay, it just assigns a numerical value to a random process. Okay, so random variables can fall into two types. They can be discrete or continuous. What this means, discrete means that the number of possible values that the random variable can have can be listed. There's few enough of them that you could write them down in an ordered list, right? So this would be the case with a die roll. What are the possible outcomes that I can get when I roll this die? Well, I can only get the numbers 1 through 6, right? 1, 2, 3, 4, 5, 6. I can list them. If you can list them, it's discrete. Now, sometimes there's so many values that you can't list them. In that case, it's continuous. This would be the case if we do the distance the die rolls from the edge of the table, or the edge of the screen in this case. There are so many possible distances, I couldn't possibly list them all. The die could land here. Maybe that's 1 centimeter. It could land here, 1.5 centimeters. It could land here, 1.3 centimeters. It could land here, 1.216534 centimeters. There are so many possibilities. If I was to try to list them all, someone could say, oh, no, you could, between that value and this value that you listed, there's a value in between that you missed, right? So it's impossible to list them because there's always something in between that it also could have been. So if the number of possible values is so numerous that you can't list them, I should say, then we say that the random variable is continuous. So that's the difference. If you can list the possible values, it's discrete. If you can't list them, it's continuous. So the time it takes the die to come to rest. Well, if I was measuring it with a very accurate stopwatch down to the nearest millisecond, there's probably too many values that I could possibly list. It would be considered continuous. If I chose a random person and measured their age in years, if I just rounded to the nearest year, I can list those, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 200 if I wanted to go up to 200. I can list all those. There's a lot, but I can list them. So that's discrete. Salaries, if I round to the nearest 1,000, I could list all the numbers, multiples of 1,000. Weight, if I measured it very accurately down to the nearest fraction of a gram, too many values to list. That'd be continuous. Shoe size, well, I can get 4, 4.5, 5, 5.5, 6, 6.5. I can list those, right? There's few of them, enough of them. They're sparse enough that I can list them all. So that's how we determine whether a variable is discrete or continuous. In this section, we're going to be focusing on discrete. We won't get to continuous until later. Okay. So what else can we say about these? Well, when we have a random variable, we can talk about the probabilities that it attains any given value, right? So if I want to know the probability, say I roll a die, right? And the random variable measures the value of the roll, right? I want to know the probability that the die roll comes up 4, right? Well, there's two ways I can write this. I can say the probability that x equals 4, because x is my random variable. That's one way people write it. Sometimes they'll just be even shorter about it and just say probability of 4, right? Understanding that we know what the random variable is. Now, if there's more than one random variable, you'll want to do it this way, because this illustrates which random variable you're using. If there's only one random variable, you can get away with this, because if there's only one, we know which one we're talking about, right? And so that's how this works. You can also talk about not x equaling something, but x being satisfying an inequality. I could talk about x being less than 4, or less than or equal to 4, or greater than 4, or greater than or equal to 4. So we can talk about those probabilities as well. Okay? So let's take a look at just some examples of probability distributions. One of the things we can do with a random variable is we can look at all of the possible values, and together with the probability, hey, I'm peeking up here, I'm getting out of the way, together with the probabilities that they occur. So the distribution is all of the values of the random variable, 1 through 6, together with the probabilities. So if I put those together in a table or in a graph, that's called a probability distribution. All right? And this is the probability distribution for rolling a fair 6-sided die. It's a pretty boring probability distribution because all the probabilities are exactly the same. And so it makes a pretty boring chart, right? And this, when everything is the same straight across, we call this a uniform distribution. Okay? Let's look at the next one. Here we're tossing 4 fair coins and counting the number of heads. Okay? I think I can freely come back up here now. Counting the number of heads. All right, so I can have anywhere from 0 to 4 heads if I toss 4 fair coins, right? Now, what are the probabilities? Well, now they're not all the same. The likelihood that I have 0 heads is different than the likelihood I have 2 heads, right? And the distribution as a table, as a graph, it would look like this. So this is the probability distribution. Each outcome together with the probabilities. Here we have tossing a single coin repeatedly until I get heads. So here we have all the possible outcomes. Now actually it doesn't stop at 7. It actually keeps going out to infinity, because there's no limit to how many times you may have to toss that coin before you get heads. You could be there all day tossing that coin and not get heads. It's unlikely, but it's possible. So this doesn't stop at 7, it just keeps going. So there's all these different outcomes and all the different probabilities, and that gives us the probability distribution. Okay, let's look at an example. Let's use this one to measure some probabilities. Okay, so if we're tossing a coin, find the probability that we first attain heads on the second toss. Okay, so we're going to keep tossing that coin, tossing. What's the likelihood that we attain heads on the second toss? Well, I've highlighted the bar that's associated with the second toss right here. What's the probability of that happening? 0.25. It's written right there. So what's the notation here? I would say the probability that it takes 2 tosses. So I could just write P of 2, right? Or I could write P of x equals 2. And what we're seeing here from the probability distribution is that that's 0.25. Okay, let's go to the next one. The probability that we first attain heads on the second or third toss. So this is the probability of 2 or 3. Okay, well, what's that? Well, it's here or here. How do I handle ors? I add, right? So it's this plus this, right? So it's when I add those, I get 0.375. Okay. What about the probability that I first attain heads in less than 4 tosses? Well, less than 4 tosses. Here, I'm going to have to use my variable x, because I need to put a less than sign, and I need something next to it, right? So let's put x is less than 4. Okay. Less than 4 tosses. Well, here I've highlighted all the numbers that are less than 4, right? Well, I've highlighted the bars, right? So there's the numbers that are less than 4, 1, 2, and 3. So I'm going to look at these probabilities. It's any one of these, this or this or this. They're ors, so I add them, right? So I add these up. The probability ends up being 0.875 if I add those numbers. What about the next one? Probability that I first attain heads in no more than 2 tosses. No more than. So it's the opposite of more than. So more than 2 tosses would be 3 or greater. No more than would be 2 or less, right? So it's going to be these two. So I add these. And now how do I write that? No more than. That means x is less than or equal to 2. And 0.750. Let's round all these to 3 decimal places. What about after 2 tosses? I first attain heads after 2 tosses. Well, that means that I'm looking at the probability that x is greater than 2. Now, this one might seem daunting, right? Because I said that there's actually an infinite number of outcomes here. It doesn't stop at 7. So I'd have to add an infinite number of numbers, right? Well, there is a way to do that, but there's a much easier way to do this, all right? And that is to use the complement rule. Remember that the probability of an event is equal to 1 minus the probability of not that event, which the book we've been calling A prime. This is the complement rule. Here's a case where it's extremely handy, right? Because I can't add up an infinite number of numbers, but what I can do is compute the complement of this. What's the opposite of greater than 2? It's less than or equal to 2. So this is equal to 1 minus the probability that x is less than or equal to 2 from the complement rule. Right? It's exactly this. This is the opposite of that. Now we computed this right here. Look, it's 0.75. So this is 1 minus 0.75. What is that? That's 0.250. Okay. So that's how you do that one. This is where the complement rule really shines, right? It's adding up an infinite number of things versus adding up 2 things. Look at how much easier that is. Okay, and finally, the last one here. What's the probability that I first attain heads in at least 2 tosses? At least 2. That means 2 or more. Or in other words, I write this as probability of x is greater than or equal to 2. How would I do that one? Probability that x is greater than or equal to 2. Well, again, I'm adding up an infinite number of things, but we know the trick here, right? So go ahead and try it on your own. Pause the video if you need to. How am I going to do that? Greater than or equal to 2. Adding up all these green bars. Yeah, the complement rule again, right? This is 1 minus the probability of the opposite. What's the opposite of greater than or equal to 2? It's less than 2. What's the probability that x is less than 2? Well, there's only one outcome that's less than 2, and it's 1, right? The probability of that is 0.5. So this is 1 minus 0.5. 0.5 is the answer. Okay? So there we have it. I think that's the end. Yes. Okay. So that's random variables and probability distributions. Hope you learned something. I'll catch you in the next video.